Tides. We think of tides as the water going in and out at the beach. That's a real perspective from like our point of view. If we stand back and look at the earth and think of what's happening astronomically, it's really the bulges, we'll call them, bulges of water on either side. Oh, the barking. On either side of the earth, of the ocean, because of the gravity of the moon and the sun. So let's we're going to look at the patterns first of the tides. And there are three main patterns. There's the diurnal pattern. Diurnal, that word means daily. So a once daily high and a once daily low tide. Then there's the semi-diurnal. And the semi-diurnal tides, there's basically two. So two high tides and two low tides during one day, semi-diurnal. And then there's mixed, so that the sizes of the tides, the highs and the lows, are different throughout the day. So diurnal, semi-diurnal, and mixed. The tides everywhere would be real consistent, but the continents get in the way, and the topography of the seafloor is different, and the sizes of the ocean basins are different. So that changes up the tides. Okay, I found the dog was trapped in the basement. We're good now. NOAA has a really good website here that has the tides. So notice that you can only click on the bright orange states because they're the ones with coastlines. And the Great Lakes is in there as well as having a coastline. Let's click on North Carolina because that's where we are. And you'll get these funny shapes. If you zoom out, you start to get these numbers. And what those numbers represent is it's saying like data points, numbers of data points. So if we zoom in on this data set, we can get data for, say, here's Wrightsville Beach, and it will say when is the next high tide and when is the next low tide and the height of that tide. That also some weather information, water temperature, air temperature, barometric pressure, winds. You can also turn that on over here by clicking on wind and getting wind speeds, water temperature. So it's in Fahrenheit, it's in the low 70s. Pretty okay, probably pretty chilly, seeing as the air temperature is only in the mid 60s. So check that out if you want to. It will give you some tide information. Let's go back to this. There's a little video here I want you to watch. I'm going to turn my face off. I'm going to put on this video about tides, and I want to be quiet.
And the sun pulls up the water in the oceans. And this is the cause of tides. The moon influences the tides the most. So let's first look at the moon. When the moon pulls water up, it creates two bulges of water. One bulge directly under the moon, and one bulge on exactly the opposite side of Earth. The moon causes these two bulges, and it would do so even without the sun and even without the rotation of Earth. Because Earth turns, these bulges of water move around Earth, or rather, Earth moves underneath them. When there's no bulge, it's low tide. And when there is a bulge, it's high tide. Earth takes 24 hours to rotate. So it would be logical to think that all over Earth there's a high tide and a low tide every 12 hours. So twice a day. But this is not the case. The shape of the sea bottom also influences this pattern. We call this the topographical features of the sea bottom. For instance, in the Pacific Ocean there's no land, so the difference between a high and low tide is only a few centimeters. But in the small bit of sea between France and England, all the water coming from the open ocean is forced through a narrow space. This causes a huge difference between the high and low tide in Calais and Dover. This can be around 15 meters or even more. The rotation of Earth also has a direct effect on the tides. The rotation of Earth causes the water in the oceans to move in big slow whirlpools around certain points of the oceans. So together, the shape of the sea bottom and the big whirlpool currents disturb the simple two high tides, two low tides picture. In fact, there are three different patterns of tides. There are semi-diurnal tides. Semi-diurnal means half day, so twice daily. This is a pattern of two tides a day, two high tides and two low tides, and they're both equal in height. There are diurnal daily tides. So this is a pattern of only one tide a day, one high tide, one low tide. And there are mixed tides. This is a pattern of two tides a day, two high tides and two low tides, but the tides are of unequal heights.
Now let's look at the sun. The gravitational pull of the sun also creates two bulges in the water on either side of Earth. But because the sun is much, much further away than the moon, the bulges it creates are much smaller. At certain times in the month, the bulges created by the moon and by the sun line up with each other. This happens at full moon, when the sun and the moon are on opposite sides of Earth and we can see the whole moon, and at new moon, when the moon is directly in front of the sun and we can barely see the moon. This means that at full moon and new moon, the high tides are extra high and the low tides are extra low. We call this a spring tide. When the sun and the moon are located at 90-degree angles to each other, you can see this in the sky as half moon, they work against each other and the tides are smallest. We call this a neap tide. When there is a big difference between high and low tide, there is a lot of water movement, which means that there will be strong currents. Full moon and new moon are not the best times to dive.
Okay, well, so that use a YouTube channel about diving. Okay, let's look. Did that stop? Please stop. Ooh, can I make it go to here? All right, here's the different tidal patterns. Move my face over here. Okay, so the first one is a diurnal tide. That's one high and one low a day. And then the now my face is in the way again. Sorry about that. The semi-diurnal tide, where you have, it's semi-daily. So it's two highs and two lows per day. And then the mixed. Most of them are going to be semi-diurnal mix, so with two highs and two lows, and then they're going to be not the same height. There'll be one strong high, one weak one, and one strong or extreme low, and one not so extreme low. The distribution of those patterns around the Earth is here. So semi-diurnal tides are in red. The diurnal tides are in yellow, and then the mixed semi-diurnal tides are in blue. So they're just, there's hard to pick out a real pattern with those. They just are. And it has to do with the shapes of the continents, the shape of the sea floor, the size of the ocean basins. You see around the Atlantic, there's more semi-diurnal tides, and around the Pacific, there's more diurnal tides. The energy of that tidal wave, so if you go back to thinking about it, instead of just a waves coming in and out and this giant bulge that takes up half of the earth, there's a lot of pent-up energy in that giant bulge. You can think of it as one huge wave that's continuously rotating around the earth, where the earth is rotating through this huge wave. So it has a really long wavelength and a really long wave height, right? And so looking at different, in this image here, different waves, regular old capillary waves, the little waves, and then building up into wind waves and storm waves, and then the big tsunami waves. This is showing you wave periods, how long it takes the wave to go by. The capillary waves are tiny, and there's a lot of them. And then in 20 minutes, tsunami wave, right? And then the tidal waves, the wave that is the tide coming in and out, is on a cycle of 12 to 24 hours. It's huge. It's a really big wave, so there's a lot of energy contained in that giant wave. Let's look at some terminology here, just like definitions of terms you may hear when people are speaking of tides. So I went over those first two already. Tidal range is a vertical difference between the high tide and the low tide. The tidal datum, now that just depends on who's setting it, but in order for us to say what is sea level, we have to say, or if we're talking about like changes in sea level, for example, a big thing in the news and science right now is climate change and the effect it has on sea level rise. And so if you're talking about sea level rise, you need to know where is sea level. And so pinpointing that with average highs or average lows is one way to do it, or the average middle of the tide. So that becomes the tidal datum. In the NOAA, the National Oceanographic and Atmospheric Administration, sets the tidal datums, and they change periodically depending on the rate of sea level rise. Okay, the flood tide is, if you say, ooh, the tide is rising, that tide coming in is the flood tide, and then as the tide's going out, that is the ebb tide, so flood and ebb tide. And the minus tide would be a time when the water level gets below the tidal datum. So tidal datum is supposed to be set as like sea level, but if the tide goes below that, that's called the minus tide. All right. So tidal currents, this is just the rising and falling of coastal waters. Water is going to move into an area during the flood tide and out during the ebb tide. There is like a time in there called the slack tide where it's right between the ebb and the flood current, and they kind of slow and almost stop. That's the slack tide, and then they're going to reverse. Those are the tidal currents. All right, we're going to look at kind of astronomical models now, with like the Earth and the Moon, and we'll add in the Sun. If we start with a real simple model, is the best way to start thinking about tides. The Earth is perfectly smooth and covered by a single ocean. So just like a ball of land covered by a layer of water. And the Moon being like directly above the equator. The Moon is always above the same point on the Earth's surface. The Earth does not rotate on its axis, and the Moon does not move in its orbit. So none of that's true, right? So this is just making a real simple model. So here's that simple model. The uniform water layer, the center of mass between the Moon and the Earth, and then the Moon is just sitting right above the equator. So it's going to be pulling on that water mass. And so here are days. The Earth moon are going to rotate around that center of mass. So here's the center of mass here. Whoops, they're rotating around this point essentially. At day 0, and then it's going to go to day 6.8, day 13.6, day 20.5, and day 27.3. And that would that rotation around the Earth gives us a month. Okay. Two balancing forces act in the Earth's moon system. There is gravity that's drawing them together, and the strength is going to vary with location on the Earth's surface and the distance to the moon and the elevations and whatnot. There's also a centrifugal force that's trying to drive them apart because they're like rotating around, right? It's caused by the rotation about that center of mass. And the strength is the same everywhere on the Earth's surface for that centrifugal force. Okay. You have the gravity pulling them together, and then that force that is pushing them apart. And so you have to think of those two at the same time. So here is that bulge of water. This line here represents the pull of the water, the resulting water level as the moon pulls that water. It's also going to have an opposite bulge of water on the other side from that leftover centrifugal force. So two bulges, one facing the moon because of gravity, and one facing away from the moon because of that centrifugal force. All right, two bulges. So we're distorting this watery envelope. Just a little meme about gravity. The hypothetical ocean of constant depth will be deformed, right? So it's bulging out one side and the other side. The excess gravity will create a bulging pointing to the moon. The excessive centrifugal force will create a bulge on the opposite side of the Earth, pointing away from the moon. Strong enough to hold the oceans to a spinning ball, but weak enough that birds can still fly. Hallelujah. The Earth is going to rotate inside that layer of water then, and as it rotates inside that layer of water, then you get the highs and the lows at one point during the day. A point on the Earth's surface experiences successive highs and low tides, right, throughout the day. So now we're going to throw in the moon into this system. Okay, where was I? We are adding in the sun now, and the sun is going to add or kind of subtract from that bulge. If the sun and the Earth and the moon are in a line, then the bulge gets bigger, and that is going to be the spring tide. If the sun is at 90 degrees to the Earth and the moon, it is going to subtract from that bulge, kind of have its own pull, and make the tides, the high tide lower and the low tide higher, and that is the neap tide. So this is showing the spring tide, where it's pulling more with the moon, the sun and the moon in a line. The spring tide's higher. This tide is the neap tide. It is not as high and not as low because the sun is going to rotate 90 degrees from that plane of or that line of the sun, moon, Earth. Okay, here they are. So these are interference patterns, the constructive interference, constructing, adding together with the spring tide, and then the destructive interference with the neap tide, where they're kind of subtracting from each other. So the spring tide has the largest daily variation between low and high tide, twice monthly, and occurs during the full moon and the new moon, and then opposite of that is the neap tide, the smallest variation between high and low tide, and twice monthly. On this graph then, these neaps are the skinny ones in the middle, and the spring tides are the ones that have more variation here. These are spring tides, neaps, spring tides. Tidal bore. A tidal bore is a wave that occurs in rivers, and it's when the tide is forced up through a narrow area, a narrow embayment or a river mouth in microtidal areas. So take a look later. I'm not going to zoom in on these or click these links, but this shows the tidal bores in the Bay of Fundy, and then another little video about tidal bores around the world. And they're kind of tourist attractions. People surf them around the world, and they're cool. Tidal bores.